So let's get started. Couple of administrative announcements, right? The next exam is after the spring break, right? On that day, I won't be in town. So if and I have no problem if anyone wants to do it before the spring break, before they leave, or during the spring break or whatever. So if you want to take it offline someplace, that's fine, right? I'll have somebody come in here during the exam hour to give the exams, but if you would rather do it at home or someplace, that's fine. You just have to promise that you follow the rules. You take half an hour and not cheat and stuff, right? So that's one of those things. And the other one, I'll send an email more of the details, right? So if any of the homework or projects that you want to make up, any of the different modules, I'll send an email out of how you can do that. Basically, you can choose to work on a project or something to make up the exam, make up that particular module, right? And I'll give the specifics, but more importantly, I don't want you to go for, if you have, say, a 2 in a particular stuff, you want to improve that to 3 or something, right? So I don't want to go for stuff. So you would have to try to get a 6 kind of thing. So I would expect you to spend that kind of effort on doing that stuff. And the grading on that is not going to be easier than what you did before. So if there's some reason that you believe that you missed out on something, that may be a way to make up for it, right? You don't have to do it, of course. And in general, if you have any questions about grades or some things, talk to me, right? So, how are things with the paging and stuff? We're kind of going a little slower than what I had on the sheet, but that's okay, because I think these are important topics that you'd have to understand. So my assumption was, if we took more time on any of these modules, it's okay, we can get rid of the last module, because that last module is not as important as what you're doing here. And last module is usually, like other classes would follow up on that one. So if we don't touch that at all, we are still good. But the paging and stuff we need to understand enough, right? Does that make sense? Right. So there is no handout going on, because essentially whatever you had from the last class is the same. We're just continuing with what we were looking at from yesterday's class. If you don't have a copy from yesterday, I think I have some extras. I thought I had extras. Maybe not. I don't think I have extras. So I put some of these numbers up. This is not in your handout, but essentially to give you a sense of what the memory hierarchy looks like. And we have it for 3 different processors and 3 different price points, right? The middle one is what you see in your the new Apple laptop or something. So it's more of a laptop class machine. The first one is the Itanium server that we have, the XP6 machines. And the last one is the Sun implementation of the servers, right? To give you a sense of what the price difference is, the 2 processor machine, HP sells it for $40,000, right? And the 4 processor machine, HP sells it for $80,000, right? Your your laptop is nowhere close to that price point, right? And one of the main differences go towards stuff like these. Stuff like so for example, it has a L3 cache. I couldn't find out what the clock cycles are for the different other L1, L2s on the different processors, right? So there's no reason to believe that the dual core processor would have a L2 which is as fast as the one for the Itanium server. But you get a sense. The L1, which is basically running at 1 clock cycle, right? Which basically runs at almost the speed as you want it. You can make a request and get the results back in the next clock cycle. You usually have like 16 kilobyte, and some of the machines split that up into instruction and data, right? The reason is programs go through a different access pattern for instructions or data, so you have different stuff for that. And when you talk about L2 cache, which is still inside your processor, it's still fast, but not as fast as if you had to go outside, right? And you have 256 of those. and then you have L3 cache, which may be in megabytes. And off chip, you have a lot more memory, right? For example, those Itaniums have 8 gigs of main memory, right? But it's going to be a lot slower than this. So you want to keep stuff as much as possible close to your cache. And the TLBs and stuff that we talked about are rather simplistic compared to what these machines do. So for example, the Itanium has a TLB which is part in L1, part in L2, right? And it moves stuff based on fairly complicated mechanism. And you'll probably go through a little bit of that in your architecture class. Maybe not. I mean, it sounded like a hybrid of a whole bunch of stuff, right? So I wanted to get a sense of what we are trying to look at. So why it's so important, right? So if it says 12 plus clock cycles, that means for 12 clock cycles, the CPU has nothing to do. So your machine is essentially running at 1/12 the clock cycles if it's running off of L3 all the time. If it's running off of main memory, it's much slower. And if it's running off a disk, it's, forget it, right? Does that make sense? So I'd like to continue back with the what we're talking about paging and stuff, right? So the paging, the first reason why we want to do that was to change it from logical addresses to physical addresses, right? And we saw that the simple case is to have a page table where the OS would fill the page table and the hardware would have to know where the page table is, and then you'll use it, right? So it's one of the things about the cooperation between the hardware and the software. How the memory has to be allocated for the system to use is defined by your hardware. And we'll see some pictures of what the hardware can do to help you and stuff. So essentially, what goes inside the page table is entirely up to the operating system. And how the hardware deals with it, how the hardware adds and figures out all the stuff is done by the hardware. Right. So the other things I kind of alluded to in the last lecture was, when you have a big page table, you don't have to have all of them filled up and be available. So if you have a notion of a page in memory, you want to swap in or what have you, right? Some of the hardware lets you have a notion of a validity bit. You can set the validity bit to valid or invalid. And all the hardware does is, if you access a memory which is in invalid memory, it'll give you a fault. And the OS can do whatever it wants with it. So here's an example of how you would use this stuff. And again, this has to be done by the hardware, right? The hardware has to know this notion of a validity bit, which means that wherever you maintain your page table, you have to maintain this V or I notion, right? The OS will have to fill that value to whether it's whatever is appropriate for it. In the hardware, if you try to access, say, the frame number 6, right? That's invalid, so it'll give you a trap. And you can do whatever and essentially give it back control, and it'll restart from the instruction where it failed, right? So the idea here is, for this process, right? It could potentially have 7 page table entries, but these last 2 ones are not there for either the reason where it's swapped out, it's in hard disk, so the operating system consciously moved it into the hard disk, or the process legally does not have that address, right? So essentially, if the program hits 6, it comes to the operating system. Operating system has to know what to do. It can either, like I said, it could be because the OS itself moved it off to the page, to the hard disk, in which case it'll read it from the hard disk, put it into some location, allocate it, fill the entry, and let it go, right? Or if it's a program error, then you get a segmentation fault or some error given to the application. So this is one way of doing this stuff. And as we'll see, you can have much more complicated things than this later. You don't have to just have validity. You can have validity for read, validity for write, validity for execute. So if the hardware provides you more control, then you can use that to do bigger and better things, right? If the hardware does not give this control, then essentially you have to fill out the entries with something, right? But if the page table, once the page table is set properly, OS is not in the picture at all, right? If your program is running and it's only accessing frame numbers 0, 1, 2, right? OS never gets involved because the page table is all set, the process is running, and it has the memory it wants, and the thing keeps going, right? So when does the OS get involved in this process? One is when you access a page which is not in memory. What's the other time that the operating system will get involved with the page tables? Yes.
Measuring context switches and other operations.
Yeah, when you do a context switch, the OS gets involved, right? The processor only knows about the page table. It only knows about one page table that it's operating on. So when you do a context switch, it's up to the operating system to switch the page table so that the processor knows what page table to look at, right? So when you start a new process, you set the right page table and then it starts running. If you do a context switch, you get involved, you switch the right stuff. But other than that, OS is not in the picture at all. So depending on what the hardware do, we can do better stuff. If the hardware does not do anything more, then we can't do cool stuff. And we touched on the next problem in the last lecture, right? Because the page table can be extremely big depending on what the architecture is, right? So if you have a 64-bit architecture, then your page table can be fairly large. So either the page table can be fairly large, or you have such a large piece of chunks that you have a lot of internal fragmentation, right? So you have to balance one of those. But when you're talking about 64-bit architecture or beyond, there's not a whole lot you can do to keep it linear. Like it's such a large address space that you either have to have really big pages or you have to have really large page tables. And since it's per process, the more process you run, the more page tables you have. So there are three ways to solve this problem. Each one of them adds more complexity. Each one of them is not complicated by itself, but the real deal is in how to make them fast, right? So the first one is hierarchical paging. Essentially, you make it into a hierarchy of page tables, and hopefully, by doing that, you save on the page table size. The next one is the hash page table, where you hash them, and I'll go into more detail in the next few slides. And then the last one is the inverted page table, which is a lot more complicated than either of those. It's very space efficient, right? You only have as big a page table as the main memory that you have, but it's much more complicated. So let's look at the more of a detail, right? So the first one is the hierarchical page table, and it's fairly simple. So if you have a page table of 1,000 entries, then you create a hierarchy of 10, 100 page entries. So essentially, you blockade the address space so that when you want to access something, you go to the first level and then the second level. So here's an example of how you do that. So if you talk about a 32-bit processor with a 4K page size, right? So that means you're using 12 bits for the offset, and your page table number is in the 20-bit field, right? So 20-bit would be 1 megabyte, 1 million entries. So instead of doing 1 million entries, we split that up into two 10-bit entries, and so that means that there's two 1K entries. So if you use all the address space that you possibly could, this does not save you space. But if you run a smaller program, then essentially you can have only one first level. So this is how it will look like it's laid out on the memory. So the first, from the outer table, so if you didn't have anything at all after the first big chunk, there won't be entry for those, right? So going back to the previous slide, so essentially this makes it so you can have a sparser table. You only have to have the first level, whatever you need for the first level, whatever you need for the second level, and this will save on space. What would this do for performance? So what would happen now if I have to access a memory, right? I would have to first look at let's look at this graph, right? So if I want to look at some page, let's say the first one, I need to look at the first level page table to find out where the second level page table entry is to get the results I want, right? And that could potentially make it a lot slower. Now you have, so if you keep stuff in main memory, then whatever cost you had before, you are doubling it. Now you have to access one page table which has a pointer to another page table which has the actual value that you want. So if you have them in main memory, then you are making it a lot slower. If you have them in TLB, then you're not going to make it that much slower, right? So depending on, so now there is more stuff to play with. So now your caching and stuff becomes more complicated, and that's one of the reasons why the Itaniums and stuff can move stuff back and forth between L1 and L2, right? So now you have more hierarchy of stuff, right? Is that clear why this will slow things down? So now you have essentially you have one page table which points to another set of page tables which actually give you the offset for the translation, right? And this is in the critical path of every instruction and every data access, so you better make this fast. But on the other hand, it'll save you on space, especially when you go to 64-bit architecture, right? And that's one of the reasons why, 32-bit used to be, pretty common for a while. Going to 64-bit is not a trivial task of, getting a faster processor and or a processor with a 64-bit address space and letting it go, right? You have to make sure that all the other stuff are taken care. Otherwise, you're going to have a humongous page table size, and when you want to reduce it, you have all these complications. So the hardware has to be faster. Hardware has to have more caching, and the OS has to be aware of how to use this in a good fashion. So here's another way to look at just this, right? So if you have a logical address of P1, P2, and a displacement, so now you look at the outer page table, right? P1, which gives you a pointer to another page table, which gives you the value that you looked for the actual page number, right? So now you have to keep both the outer page table and the inner page table in cache for you to make good speed. So another way to go about solving the same problem, again, these are driven by what the hardware can do. So the hardware does not know about multiple page tables, then there's not a whole lot you can do. So the hardware has to know about these two page table constructs, because all these instructions are happening in hardware, and the OS is not involved in the actual how this translation happens, right? OS only sets up these tables. Hardware would have to use these tables. And that's an important thing that you should remember. OS is not involved in every translation, right? So the notion of a hash page table, right? You define a hashing function. Again, that's done by hardware, right? The figure is, I think, it's more easier to remember. So essentially, the hardware implements a hashing function that, given a page table count, you'll hash that number, right? And into this table. So you have a hash table which is a lot smaller than your original page table, right? And the hardware would hash this number and come up to an entry, right? You must have seen hashing in some algorithm class, right? So what's the one thing that happens when you do a hash?
Collisions?
Yes, you get collisions, right? Essentially, the hash table is smaller than what you really want, which means that two of the addresses can map to the same particular entry. So in this example, you have at least two of those, right? So essentially, when you have a collision, you have to search all the entries which map into the same thing. So if you're looking for P, essentially a hash function will tell you what chain you get, and then you search on these entries to find out what you want, right? So in the case of P, you have to, it's a second entry, so you follow pointers or what have you, right? Again, these are done by hardware, so the OS does not get to say what hashing function should be used or or how this, how this lookup should happen, right? So if you took algorithm class, you'd have learned about a lot of optimization you can do on following this chain, right? You can have skip list or normal linked list or what have you, right? Again, we have no control over how these hashes are set up. Whatever the hardware wants, you do that at that way. But essentially now you can make this hash table as small as possible or as large as possible. If it's as large as the page table, then you would not have any collisions. Right? Essentially, it boils down to a page table. But if it's very small, then you have lots of collisions, and the performance suffers by looking through this list. So if you have a nice sweet number, then you won't have as many collisions, and your table will be small, right? What is the one thing that decides how good a collision or how much collision you have from your algorithm class, right? What's the critical component here which will give you as good a performance as you can imagine? This is nothing to do with the OS, right? But it's more with the how hashing functions work.
Is it the hash function?
Yeah, essentially the hash function, right? No, so why I'm saying that is when you take algorithm class, you probably went through. So where did you learn about hashes? Which class?
Data structures.
Data structures. So did you spend a lot of time on hashing or?
A
Little bit. So you will take an algorithm class where you can probably go through hashing functions. People make their career on coming up with good hash functions, right? Coming up with a good hash function is not a trivial task. It depends on what you expect the distribution of the page accesses is, right? And so in this case, you expect typical programs to go through a certain set of addresses. So you want those to hash good, right? So for example, if you assume most of the programs only use from 0 to 1,000, right, for the addresses, even though you can do up to 64 bit, which is a long number, you never actually get to that, right? So a hashing function, the simple hashing function can say from 0 to 1 million should go to the first bucket, 1 million to 2 million go to the second bucket, what have you, right? And that's probably something that you would implement in an algorithm class. That sort of stuff would be terrible for this, right? Because you are now essentially moving all the programs thing into one bucket, right? So you have to build a hash function which understands what programs do, understand what programs typically do, and the play of how the programs are accessing memory goes into big play here. And that's one of the reasons why I want you for your homework project 3, right? So how many of you started with the homework project 3? Not the implementation, but looked at it and tried to see what it is, right? So more people should look at it, right? The first step essentially, I think is the most important thing. I hope that you can get out of that, right? The first step basically lets you capture the logical addresses used by any program, right? So it essentially captures all the logical addresses made to that caused a failure, that caused actually not a trap. So all the accesses, both the instruction and the data, right? So I want you to run it on some program, right? And you'll notice that it tends to be very large very quickly, right? So I have 2 traces. So look at the first trace. I think first trace was for echo command. So it essentially does practically nothing, and it's like 1 megabyte or something, right? So if you look at that, that's what all these people want to look at. They want to see if you run echo program, what is the sequence of addresses that program generates, right? And if I can make my program look really, really good for those set of addresses, then the users would be happy, right? So you're not trying to optimize you're not trying to create architecture which will perform the best on average. You want it to make it look good on typical programs, right? And you can define typical programs as your benchmarks that people use. And some of you may have heard of like spec benchmarks and other stuff that companies say how good their machine is, or what have you, right? So, but look through those programs to see if you see any pattern, like see how those things are, and that addresses essentially plug into this hash function that can tell you how good this, your particular program would work with a particular hash function, right? So the second part of your project is to try to do something with those addresses, but at least at this point you should know enough to look at those addresses and make a sense of how these things look like, right? And all the things we talk about, page tables and all those things, are stuff that the programmer looks at. From OS perspective, your trace is all that the OS sees. Sorry, from the machine perspective, that's all it sees, right? Machine does not care what you do with the memory location. All it knows is you're accessing all this memory, and it should make it faster, right? So I very strongly encourage people to just run the first part and just look at the addresses. I'm not saying you'll make any sense out of it because it's probably billions of lines long, but it gives you a sense of how these things are progressing, right? So that's one way to save on the page table size, and the last one is the most efficient in terms of space, but it's more complicated, right? So essentially, previously what we had was for every logical address you had one page table entry, right? So you had a fairly large logical address space, you have a fairly small physical address space, right? And the page table mapped from logical address space to the physical address space. It mapped from a very large address space to a very small address space. So your page table entry was large. In the inverted page table, right, you invert it upside down. So essentially your page table is as big as your main memory, right? Or every page in main memory has one entry in this table. There's one table per machine, per operating system, right? So it'll keep track of what is the logical address which is currently residing on that particular page, right? So it's the opposite. So when I want to use this paging architecture, I want to figure out, given a logical address, what's the physical page it is. What this table maintains is, given a physical page, where is the what's the logical address which is on that page, right? So the page table is not keeping track of what I really want, but it's keeping track of what is easily available to it. And you basically have to search this table to find out what the number is, right? So again, I think the picture is a lot easier to use. Now you have to have a notion of process IDs. You need to have a way to figure out what process is actually using it, because all this table has is, for every physical page, what is the logical address which is stored there, right? And this logical address belongs to a particular process. It's not a logical address for the entire machine. So it basically says that, the physical frame I currently stores the logical address called P for a process called PID, right? So this table only has to be as big as the amount of physical memory that you have. And most likely physical memory would be much smaller than your logical memory, right? Because your physical memory on a 64-bit processor, like I said, that machine is 8 gigabytes, which is fairly big, right? And you can think of like 64 gigabyte. I think the maximum you can put in the machine is 64 gigabyte, right? Which is nothing compared to a 64-bit number, right? How big is a 64-bit number? I don't know how to say it, right? But it's so what is the? It's a very big number, right? I've seen estimates which say that I think all the atoms in the known universe can be in 2 power 78 or something, right? So and 2 power 64 is not that big, but very big, right? So it's highly unlikely that we're going to have that much main memory anytime soon. So your page table would be large. So even 8 gigabytes is nothing compared to this bigger number, right? So doing this, you would save a whole lot on memory, right? So the other nice thing about this is there's only one page table for the whole machine, right? It's not process dependent. It depends on how much physical memory you have. So when you do a context switch or whatever, you don't have to switch page tables. There's one page table for the whole machine. And it essentially has to have a process ID or something, right? So it does not have to be a process ID. It could be a unique number, right? You also need another register for the CPU to have, which should hold the unique number, right? So what it does is every time you do a memory access, you'll try to see if the contents of this unique is the same as what is in this page table, right? If it matches, then it knows it's the right process, right? So you can use process or you can use something random. So the hardware now has to have this notion, which basically says what process is running on the machine right now, right? In general, right? Do you think that the CPU knows about the concept called processes, or does it not? In general, forget about this. Does the processor know what it's doing? Yes. Yeah, the processor does not know whether it's running a process. It's running instructions. I mean, it's going through instructions, and instructions could be from a process or thread or whatever abstraction you have up there. So the processor does not know about process IDs or processes at all. Except in this case, you need to have this notion because otherwise anybody can run anything and anybody can access anything, right? So it's more than protection. It's also making sure that only you have access, right? So the key thing to remember here is you have only one table for the whole system, right? Even the hierarchical ones and the hashed ones, they are one per process, whereas here is one per machine. But the price you pay for that is when I have to. So now, what would have happened is this P, the process P, the page table P, was essentially in physical address I, right? But I don't know what I is. So you have to look in this table, search in this table to find out where this P is, right? You may have to search the whole table, and whatever searching algorithm you would implement, right? And this is implemented in hardware, so it's not something that you have control over. So essentially, it has to search through this table to find out if there is any entry which has a P in it, right? If it is, then the index of where it is the actual location where the physical page is, right? And this calls out for something like associative memory, right? Associative memory does basically this. You can look through all at once and tell you where the entry is or how to get there, right? Except you can't really implement associative memory of this bigger size for any reasonable cost, right? So hardware will go through and trying to figure out how to do that. So is it clear how the inverted page table works? So if you think that inverted page tables are harder, I'll go through what Intel 386 does, and most of the other things I talked about probably do much more complicated than that, right? So before we do that, we introduce a notion of a shared. So let me add one more to the inverted page, right? Inverted page, one of the good things is there is one table for the whole machine, right? The bad thing is sharing pages is a lot more harder, right? Because now that you're sharing through like a process ID or something, if two processes want to share the same thing, somebody should make sure that the right process will have the right PID, right? The PID that I have. So if two processes are sharing something, they both should have the same process ID or some unique number or what have you. And if you do that, all the pages from both the process would be essentially shared, right? It's very hard to kind of say we have two processes here, right? P1 and P2, right? And they will share this by themselves, and there is basically a different size here, right? If they don't want to share something and they want to share some of it, right? Implementing that using inverted page table is a lot harder, right? The only way you can do that is if you have one unique number between both these processes. But if you do that, then essentially you have access to everything, not even the ones that you don't want to share, right? Can you fix this somehow by making this unique dynamic? Can you make this unique number only unique while you're sharing and not unique when you're not sharing? That would be one way to fix it, right? Essentially, if you know that the process is going to access something here, then you leave something which is the same. When you know the process is going to access something somewhere else, you could use a different unique so that they don't share, right? Could you do that? Can't I actually answered it a little bit back of what the OS does, or what is the role of the OS and what is the role of the processor, right? Somebody's kind of trying. Is the question clear? Right? So let me say the question again, right? So if two processes were to share something, they have to have the same process ID, right? And same process ID means they are the same process. It's kind of boring. So one way to change this is to the processor does not care what number you call. All it wants to make sure is that that number matches some magic register which is elsewhere, right? So what we can do is these two processors which are sharing something can set a same number, a same unique number, right? Which essentially means that both the processors can access that shared page because they both have the same unique number in this magic register. So when the processor looks at the stuff, it sees the same number, it'll let it go, right? So the sharing part happens. What also happens is the stuff that you don't want to be shared also gets shared, right? Because now this unique, so if this process wants to access this, if it were to make a pointer to this, right, you essentially have the same unique number, so you will share. So essentially, you share all or you share nothing, right? So I was asking, is there a way to fix this problem by selectively saying, while the processor is accessing this, I would have the unique set to something. But if the processor tries to access this, then I would change this to, say, unique 1 or something. So process 2 cannot access this stuff, right? Can you do that? Yeah.
You would almost have to interrupt the system with a context switch or something, so that you could change the addresses, but when the program is executing, you're not going to be able to change without interrupting it somehow.
Yeah, so this goes back to the same thing I was saying before. Once you set all this stuff up, once you set the unique register, once you set all this stuff, the OS has now no control over the machine, right? The OS does not get involved at all, right? So it has no way of knowing where it's going, right? All the sharing and all those things is a figment of the OS's imagination. All the sharing concept, everything is a figment of the OS imagination. Processor does not really care, right? So if you don't get control back to do that, right? There is one way to get control back, and I'll kind of say it, and we'll use that in the future for other stuff, right? Which is, every time you access a page, you can change the mode bits, right? So you can make the page, all the pages invalid all the time, right? So every time you access a page, you get a page fault. And the OS can decide, okay, it's for a shared page or non-shared page, and set the bits at the right way. right? That's one way to do that. We'll use that for something else later on, but essentially that's what you can do. You can change all the pages to be always invalid, so every memory access will come to the CPU. That machine will be so slow, right? It can hardly move because every instruction will get the operating system. Operating system has to do something and then let you go. The next instruction, you get the context switch, right? So it's not a practical solution because everything gets done, but that's what happens. So if nothing, remember what role OS plays and what role the CPU plays, right? And that's very important because there are some things you can't do because OS is not involved. There are some things you can do because OS is involved, right? And that's essentially the crux of all the paging stuff, right? So but you do want the notion of a shared page, and so you want so some of the text segments and stuff, you want it to be shared because they don't change anything, so you can reuse the same stuff. So you have an example of 3 processes. One is in blue, one is in gray, and one is in white, right? They all access the same 3, 4, and 6, right? Which are the same, let's say the program, right? So you're running the same program 3 different times. So the same program text, in the code is the same, only the data changes. So all of them have different data. So the blue one has the data 1, the white one has the data 2, and the gray one has the data 3, right? Which means that the page table entries for those, the page table entry for the 4th entry is different. Everything else is the same, right? It's up to the operating system to do that. So when processor P1 is running, it essentially accesses the same shared page, and processor 2 accesses the same shared page, right? So you have 3 page tables. Part of the page table is the same. If you look at the page table, the first 3 entries are the same for all the 3 cases, right? So in this way, you share the same piece of actual memory for whatever you want, right? You can do more complicated stuff like by saying shared read only, shared write only, or execute only, and combinations thereof. But that's the idea, right? So I'm going to kind of breeze through the notion of segmentation because we're kind of running late. So the idea of segmentation is when you write a program, programs don't really think of pages. They look at it as a concept of segments or chunks. They want to say as code. They want to see it as memory locations or what have you, as variable size construct, as something that they allocate. So sort of like this, in your logical address space, you want to look at it as function code and main programs and symbol tables and what have you. Compilers generate these kind of the constructs. And these are all variable size, and so you need to map this to a paging architecture, right? In this way, you have a notion of external fragmentation and all the stuff we looked at before, but the actual implementation won't have those problems, right? So another way of looking at it, so the segment 3 that you look at may actually be larger than segment 2 in main memory, right? So I'm not going into detail because it's essentially what we did with the contiguous allocation problem, right? You have to have a notion of where's the start of the segment, where's the end of the segment, what have you. You have to have a notion of relocation, you have to have a problem of allocation, all those things. What is important, and you also have a notion of some. I'm going to skip through, but essentially it's the same as what we did before. I'll quickly go to the part which is different, right? You have, you can set permission bits like I talked about, and we'll see more of that later in the course. So, at a conceptual level, you try to do the same thing. You have we looked at that before, right? Limit and the base address. So every address would have to figure out what segment it is, try to figure out if it's within the limits of the segment, and let it go, right? And examples of how the segmentation table would look like a page table entries and stuff, right? So, this is the interesting part. So the programs want to have a notion of a segmentation, and it has all the problems that we talked about in contiguous space. What operating systems try to do is map the notion of segments into what the paging hardware does, right? So one of the oldest operating systems, Multics, which is kind of the father of Unix, right, implemented segmentation on top of paging. Essentially, each segment would have its own page table, right? The CPU knows only about page tables and page table entries. Every segment has its own page table. So sort of the pictorial representation is like that, right? So when you create a logical address, you figure out what segment it belongs to. You do the checks whether the segment is within the bounds, right? And that gives you a whole set of pages where this segment would map into, right? And you have a page table for those. So you get the page table base, and then you do a page table translation as if that's the only things you have to get the actual memory, right? So this way you can get the best of both worlds. Your program thinks of it as segments, but actually implement it using paging, right? So you go through a first level of paging and then a second level of, first level of segmentation, second level of paging. And of course you can make this, the second level, more complicated. So you can have first level of segmentation and second level of hierarchical paging, right? Which is essentially what your 386 does, right? Your 386 architecture is a segmented architecture, so it knows about segments, right? So you go to the segment tables to figure out the page table entry, and the page table entry that you have is a 2-level entry. So your translation would take a segment register value, does all the bound check, right? Comes to the second part, and the page table at that level is 2 levels. So essentially, you would have to look through 2 of these to figure out what the logical address space is. And this is for the 386, right? And this is one of the things I mentioned, that if you look at the itanium and all those things, it's more complicated than this, right? So you don't actually do one of those. You do variants of this because you want the best of everything. You want the naming to look like what the applications would understand, like segmentations or whatever. And paging is a lot more efficient in terms of implementation and fragmentation, and then you have to worry about, multiple levels and stuff. I'm going to end it at that, but the little thing about Linux, Linux tries to find the lowest common denominator. It doesn't try to push the hardware as much as possible. So, sorry to tell you more, but see you.